All right, we're going to continue with the metathesis reaction. The metathesis reaction, we're just looking at what ions like each other and want to combine to react. And certain ion combinations. Those ion combinations result in precipitate gases or weaker acids or stronger acids. The other types of reactions that we look for, or redox reactions. So I just want to talk about redox reactions. This projector is not working, so I'm just going to do this on the board for the redox reactions. Redox reactions, we have certain types of redox reactions that we cover. You probably covered like element plus element combination reactions, something like this. If we have magnesium, magnesium solid reacting with oxygen gas, what form? Well, what forms is magnesium oxide. We call this the oxidizer over here. This is going to be the reducer here. And when this reacts, magnesium will lose 2 electrons, oxygen will gain 2 electrons, so we're going to form MgO solid. If you'd like to write the charges, don't write them in the formula for the compound. Compounds are neutral. You can write the charges for the individual ions and then balance it out that way. And so what we need is we need to balance this. We can balance this by using fractions or whole numbers. So I could do half an O2. It wouldn't be half an O2 molecule, but it'd be half a mole of O2. Or this is double everything. This gets complicated when we have a choice. For example, if we have copper and oxygen, what do we form? Do we form copper 1 or do we form copper 2 oxide? And normally you would just go with the ones that are most common, the charge. What charge on copper is most common? Do you know? Copper 2. Actually, you can see this. This is what we call a redox chart over here. We call it the redox half reaction chart. We're going to be using this for redox reaction. So when we look at copper here, it goes to copper 2. And then we look for other. Do you see any other coppers? No. And so this redox is an abridged chart. They can't be comprehensive. And so we're going to put the most common charges here, the most common reactants. And so in this case, this is going to be copper 2. We would expect it to be copper 2. In reality, what happens? If you have a shiny new penny, it goes through a range of colors. A shiny penny will first turn like an orange red as it becomes oxidized. That orange red is copper 1 oxide. And then eventually it turns black. The black is copper 2 oxide. So in reality, both form. Eventually it stops at copper 2 because the penny is going to be completely oxidized. So what we want to do is in these types of reactions, metathesis and was I supposed to? No, redox. Yeah. Did I go metathesis, redox? Gotta look at my PowerPoints again. But basically, we just take it to completion. It's like when you do combustion. When you combust something, you might not combust it completely. If there's not enough oxygen, you're going to form a lot of carbon monoxide, you're going to form a lot of soot, right? But we aren't going to worry about the carbon monoxide. We're not going to worry about the soot. We're going to assume that we're going to react it to completion. We don't want this halfway reaction or partial reaction. We're just going to go all the way. And so in this case, we're going to just take this all the way to copper 2 oxide. Solid. And so this is element by element. And the element, you can figure out the charges once you know the charges on the periodic table. The variable charges and the fixed charge. Fixed charge is easy. This is what you'll have in Chem 4. Variable charge is it's a little bit more difficult because multiple products are possible, but we just assume complete reaction. And then we had single replacement. Single replacement is easy because it has the A plus BX type pattern. Right? The A plus BX pattern, the situation with that is There's more patterns. What's another single replacement pattern? Did you learn all the patterns? Did you learn the x2 plus ay pattern? Did you learn the exceptions? You know, did you learn when single replacement doesn't work? That's a problem. You know, it's okay, like in Chem 4, it's okay to give you certain types of problems that that you don't have to worry about those exceptions. You know, it's like this. When you know, if you have a small child or something, you put them in these little fenced-in play areas, right? Well, that's like Chem 4. You're in a fenced-in play area. The only things you have access to are what's given to you. And so the type of problems that you encountered in Chem 4 are the types of problems that work with single replacement. But what they didn't give you are things that don't work with single replacement. So for example, this, silver solid plus HNO3, you would predict using single replacement, you'd predict no reaction, which we call NR, no reaction, but that's wrong. There is a reaction here. It's just not of the single replacement form. That's it. And so there are exceptions,
You use the activities series, right?
You use the activities series. So if we did this by an activity series, we'd be comparing, this forms silver nitrate plus hydrogen. We'd be comparing the activity to hydrogen versus silver. What would you rather have your trunk filled with, silver metal or hydrogen gas? What do you think is more stable, less? Silver metal. So then you obviously you don't want to go to hydrogen gas because it's less stable energetically. We use the activity series. Therefore, we would say that there's no reaction. But if we say no reaction, well, that turns out to be wrong. And so what you have to do is you have to memorize certain things. If you like the single replacement form, you have to memorize the exceptions. One of the exceptions is this type of acid. This is a special acid. This acid is called an oxidizing acid. Single replacement fails for oxidizing acids. For mineral acids, it works. Like if this were HCl, no problem. HCl is what we call a mineral acid. And so what's the difference between an oxidizing acid and a mineral acid? Well, in a single replacement form, you know, the oxidizer, A, is the reducer. B plus Z is the oxidizer. X minus Z is the spectator. It turns out that nitrate is not a spectator. In fact, if we compare the oxidizing strength of A, which is H+, actually this chart does it for us. This chart is the strength of the oxidizer and the reducer. And so we're going to get familiar with this chart. When we use this chart, we need to memorize two reference points. One reference point is fluorine, F2. The other reference point is lithium, La solid. On this chart, the oxidizers are written on the right-hand side. On the chart I gave as on Piazza, the oxidizers are written on the left-hand side. On the chart on Piazza, you'll see fluorine at the top left, lithium at the bottom right, but it doesn't matter what the orientation is. As long as we remember fluorine and lithium, it can be upside down, right side up, you know, on its side. It doesn't matter because you always have your orientation. A lot of people, when they think about orientation, they think, okay, you know, top. It's at the top left. Well, at the top left, that could be different if you're out in space. Is there a top left or a bottom right? There's no orientation if you're out in the middle of space. And so what we need to do is we don't think in terms of top left, bottom right. We think in terms of fluorine and F2 and lithium. You memorize those. Well, what's special about fluorine and lithium? What's special about fluorine and lithium?
Electronegativity difference?
The fluorine is highly electronegative, meaning it wants electrons. It really wants it. In fact, it's the most electronegative species, making it a very powerful, what we call powerful oxidizer. And lithium is the opposite. Lithium has a very low ionization energy. In fact, lithium doesn't have the lowest ionization energy. If you look at the activity series, which of these species has the lowest ionization energy? Lithium, rubidium, potassium, calcium, sodium, magnesium, aluminum. Look at these. Which one has the lowest ionization energy based on your Chem 1A? Which metal is easiest to ionize? Rubidium? Well, if we take a look at the chart, you would be right. Rubidium on this chart over here, based on the periodic table, look at the periodic table for this, would be the easiest to ionize. Why?
It has the largest radius.
Yeah.
Atomic radius.
This is large. So, you know, lithium is actually very small. These electrons close by. And so what an oxidizer does is comes and plucks the electron, the outermost electron. And so what's easier to pluck an electron? A small, tiny lithium or big rubidium? A big rubidium. And so rubidium is going to have the lowest. So why isn't rubidium the most powerful, what we call reducing agent? Reducing agents lose electrons in redox reactions. And so rubidium should be the most powerful. It's not, however. And so this is one of those things that, you know, people who never look at the chart, you know, all of a sudden will get hit one day with a question. Hey, why isn't rubidium at the top? Why is lithium? You know, and a lot of people, they never think about this, and then all of a sudden they're total loss because they haven't thought about it. Right? And so this is why you want to think, or at least read the entries. Yeah, by reading the entries, or you don't have to memorize it, but you read the entries, and you really, does it make sense to you? Because those are the typical questions. When things don't make sense, people ask questions. If somebody's going to ask a question, why is rubidium at the top of the chart? What would you tell them? You can tell, I don't know. That's the way it is. That's fine. You know, that's a fine answer. You don't have to know everything, of course. You know everything. But can somebody tell me why rubidium is not at the top of the chart? Rubidium certainly is the most reactive and the most dangerous of these, I'll tell you that. Even though it's not at the top of the chart, lithium is a much more mild manner. Using agent. Although mild mannered is not really the word to put on it, because lithium battery catch on fire all the time. Definitely explosive. There's a lithium battery plant. There's a lithium battery plant in Japan that's completely destroyed by fire. I have to verify it, but they sprayed water. Do you want to spray water on a metal fire? Yeah, you never spray water on a metal fire. Even though water is stable, right? The water is a mild oxidizer and oxides metals. Anyway, let's go back to this. Does anybody know? In terms of sheer reactivity, rubidium is. In terms of energy stabilization, lithium is. And whenever we have a reaction, there are two parts to the reaction. One part is how reactive are the reactants. The second part is how stable are the products. It turns out rubidium is a much more reactive reactant, but it has a less stable product. Rubidium ions are less stable. You know why rubidium ions are less stable than lithium ions? This is
Because heavier noble gases can't react and stuff. Okay.
No, it's not because of that. It's because what we're forming is aqueous solutions. We're forming aqueous solutions. So why would aqueous lithium ions be more stable than aqueous rubidium ions? It goes back to chapter 14. It has to do with something in chapter 14. In chapter 14, when you dissolve a solute into a solvent, thermodynamically, what are the three processes, the three steps in terms of energetics? Well, you know, actually, in an effort to save time, we could keep moving here. It has to do you know what the solvation energy or hydration energy is? When you dissolve a solute, step one, delta H1, you break the solute-solute interactions or bonds. You know, and then step two, you break the solvent-solvent interactions or bonds. Step three, you form the solute-solvent interaction. Okay, so step one and step two, energy goes up. Step three, you have a big drop in energy as you form solute-solvent. If the solute-solvent interactions are favorable, then it's good. And so what we're forming here is we're forming what we call ion dipole attractions. It's the ion, the charge, plus one, being attracted to the dipole of water. The water molecules surround this in what's called a hydration sphere. Typically, when you look at a hydration sphere, you can fit about 6 water molecules around each ion. And those water molecules are going to point to favor the electrical interaction. Oh, actually, look, they fixed it. Maybe, you know what, I'm going to go back to PowerPoint. Let's just save time. Speed things up. Oh, that's great. Okay. So what am I talking about? Let's see.
Oh, it's not.
Oh. And so what we set up are these ion dipole attraction. Although let's see if we can get a decent three-dimensional, not three-dimensional. Decent. So obviously we have our hydrogen bonding interactions between the water molecules, and these are very strong, right? The strength of these hydrogen bonding interactions are about, somebody know roughly? The strength of these are about 25 to 50 kilojoules per mole. How does that compare to an actual bond? Is a hydrogen bond an actual bond? And so where do let's see what's about the weakest covalent bond? How does a hydrogen bond compare in energy to a covalent bond? Is a hydrogen bond an actual chemical bond? Would you say no? It's an intermolecular force, but it's fairly strong at 25 to let's say 25 kilojoules per mole or 50 kilojoules per mole. What's a weak bond? What's the weakest chemical bond you know? Any weak bond, easy to break. Some of the weaker bonds. What's one of the, how about what's one of the strongest? Tell me what's the strongest chemical bond that you know?
Ionic?
Ionic bonds are strong. Well, how strong? Ionic bonds, the strength varies though quite a bit.
Covalent network.
Covalent network are strong, but covalent you're looking at breaking a mole of a particular type of bond, so it depends on what the bond is in the covalent network. So some covalent networks are quite strong. The lattice itself is going to be, but still there's some bonds that are very hard to break. There's one molecule that we deal with every day.
Water.
No, water. The bonds are pretty strong, but not that strong. Something much stronger than water. Bonds. You deal with every day. That's a very strong bond. Covalent bond. What do you think is strongest? Single, double, or triple?
Triple.
Triple bond. It has a triple bond. What is it? Well, I love to talk about Chem 1A stuff, but I have to break this habit. Otherwise, we're not going to get to the Chem 1B stuff. But the strongest would be, on an everyday basis, the strongest would be nitrogen. The nitrogen triple bond is so strong, they call nitrogen gas a pseudo-noble gas. That's relatively inert. It doesn't react with much, right? And that's about 1,000 kilojoules per mole. Some of the lattices, like magnesium oxide or iron 3 oxide, those lattice energies are huge, over 2,000 kilojoules per mole, for some ionic compounds. But the weakest covalent bond would be a single bond. And for example, the weakest are around 100 kilojoules per mole. 100 kilojoules per mole is not all that much stronger than this, right? 4 times, 5 times stronger. But it would be like a weak bond would be like a household chemical, like peroxide. Hydrogen peroxide has a very weak bond. The oxygen-oxygen single bond can easily be broken by visible light. Iodine. If you have iodine, you don't store it under visible light. This light is going to break that bond. It's got a weak bond, 100 kilojoules per mole. Well, anyway, these ion dipole are very strong. Some of these ion dipole interactions, shown in green here, really stabilize this. Because if you think, the sodium chloride lattice, to break that apart costs about 700 to 800 kilojoules per mole. And so if you have some salt, table salt, and you want to break it apart to dissolve it in water, you got to spend 800 kilojoules per mole to break the lattice apart. Technically not that, because lattice energies are breaking apart the lattice to form gaseous ions. We aren't forming gaseous ions. Okay, so we break it apart, and then you got to separate the waters. Separating the waters is another, how much? 25 kilojoules per mole to separate the water. So now we're at like 800 kilojoules per mole just to break apart the sodium chloride, to break apart the water. Why the heck would sodium chloride dissolve? It's going to cost you 800 kilojoules per mole. Right? It makes no sense. You're going to go up in energy 800 kilojoules per mole. This is why you got to know the numbers, because somebody who knows the numbers is going to say, hey, it doesn't make sense to me. You're telling me it's going to cost me 800 kilojoules to dissolve salt in water. I don't believe that's going to happen. Now you have to defend your position. If you tell me that salt is soluble in water, right? This is what happens in science. In science is the scientific method, and science in general is it's kind of like this self-policing organization. All the junk science, all the fraudulent science is easily filtered out, because scientists are very critical in that sense of everybody's results. And so when you present your results, they're going to ask you lots of questions to make sure that they can trust your thinking. Does that Does that make sense? Because otherwise, people are coming up with perpetual motion machines. People are coming up with new forms of this or that, that have supposed benefits. A lot of it's total junk, and that's filtered out. It's filtered out by people doing questions. This is why in science, this is why some professors, they don't care about cheaters, because eventually they're going to be filtered out with the rest. And so, in science, that's what happens because of the way it works. There are a lot of charlatans in science that come around. But anyway, the reason it works is because of these green interactions. These ion dipole are very strong. In fact, if we look at the thermodynamics of this, I don't know if you recall, there's a figure in the book. Since this is working, I'll just show you the figure from chapter 14. This is important because we went out of order a little bit. So let me talk about this. Boy, they didn't fix this. These are new computers. So slow. Well, basically the figure in the book is like this. Okay, we have delta H1, which is breaking the solute, 800 kilojoules per mole, let's say 700 kilojoules per mole. Then delta H2 would be breaking the hydrogen bonds in water. And so altogether, this is going to be about 800 kilojoules per mole. And so this is becoming less and less stable, right? The stability is going to come from delta H3. Delta H3 almost brings us back to even. Almost brings us back to even. Delta H3. Yeah. But you see that there's a little bit of energy. We're going up in energy. Is that okay? In order to dissolve sodium chloride, so what we end up with here is we have sodium chloride solid, and then we're going to sodium chloride aqueous here. It's endothermic. Did you know dissolving sodium chloride is what we call endothermic? Endothermic processes require energy. This is like this. This would be endothermic, lifting up the ruler or meter stick or whatever. This would be endothermic because this costs me energy. I mean, if I let it go, it doesn't cost energy, right? That's fine. And so the question is why does this happen? In physics, does this ever happen? Would I ever have to worry about this pen shooting up and hitting me in the face? Would I ever have to worry about that? Is there a rare chance it could happen? It could just shoot up, and hit me in the face. No. But here, this is what happens. This is endothermic. Why does that happen? Salt shouldn't dissolve. It's like this pen. Salt dissolving is like this pen shooting up in space and hitting me in the face just at random. Just if I let it go, I got to keep it on the table because if I let it go, it'll pop up. That's what happens with sodium chloride. You let it go in water and it pops up. Why? There's no spring there. Well, maybe this isn't fixed after all. Try this question. Oh. Thanks. Well, it's not a big pop because it's only about 5 kilojoules per mole. Is 5 kilojoules per mole all that big? 5, 6, 7 kilojoules? That's small. So maybe it's okay. Maybe it's like this pen. It just pops up a little bit. I don't have to worry about it hitting my face, but it's going to pop up a little bit. And so I don't want to put my face down on the table because it might pop up and hit me in the face. It's just a little bit, right? Well, the reason why we could even think of this dissolving is because of this. And that's the reason why that lithium is at the top. Lithium shouldn't be at the top, to be honest. Lithium is a lot less reactive. The only reason lithium is at the top is because of lithium ion. What's special about lithium ion compared to rubidium ion?
It only has one shell.
I'm sorry?
It only has one shell.
Okay, but yeah, so what does that make it different? How having one shell would make it different than having multiple shells?
I would assume because it only has one shell, it absorbs electrons easier.
Not exactly. I mean, in a way, yes. In a way, it wouldn't absorb electrons because if there's any oxidizer around, if the oxidizer is usually more powerful than lithium, and so it loses electrons. So, it only has one shell. That has an important implication in terms of,
It has more affinity than rubidium.
Okay, yes, it has more affinity. Well, I don't like, I don't like the electronegativity or attraction for electron. You should just say it's positively charged and it has a higher, lithium ion should have a higher. Okay, if it has one shell, it means it's smaller. And so what I was looking for is this. If it has multiple shells, it's big. If it has one shell, it's small. So the difference is, in the way chemists think in terms of Coulomb's law. Coulomb's law says this: charge, right? The higher the charge, the more reactive. And size are important. Charge and size are, so when we think in terms of size, how big is it? And what's its charge? Because we're looking at these interactions. In chemistry, all we deal with are electrical interactions. Let's see, I'm at 11th picture. So we're unfortunately in the blue scenario with sodium chloride. We break the solvent, solute. I had it back right there. I took the solute. It doesn't matter. We go up, we go down. For sodium chloride, we're blue, so it's endothermic. For an ideal solution, what we call an ideal solution, the interactions between the solute, solvent, and the solute solvent are the same. So this is what we call an ideal solution, black. And the red is favorable because the red is exothermic. When we form a solution and it releases energy, that's energetically favorable. So dissolving sodium chloride is energetically unfavorable. So why is sodium chloride so soluble? That's the question. What's driving this? What's the driving force? But I'm getting ahead because this is the next thing we're talking about in chapter 13. But what we have here is the reason why it dissolves is because we're forming these blue interactions. What are those blue interactions? And the blue interactions, the more favorable, the better. And so the blue interactions are shown in the red here. But I'm going to show a better picture. Okay, what is an ion dipole interaction? Is attraction between the positive cation and the delta negative of the water. It's an electrical attraction. What dictates electrical? What describes electrical attractions? Coulomb's law. In terms of Coulomb's law, we're interested in two things. One, the size or the distance, and two, the charge, the magnitude of the charge. And so here, that means the difference is lithium is very small, rubidium is much bigger. And so the difference between lithium ion and rubidium ion is what we call the charge density. What's the difference in the charge density? Which one has a greater charge density, lithium or rubidium? Lithium. And so because of lithium's small size, its interaction here is very favorable. That means it forms strong ion dipole attractions, which means these are very hard to break apart. In fact, those ion dipole attractions are what makes lithium the best reducer. It's because of how stable the product is. When we look at chemical reactions, we're always looking at the stability of the product. The more stable the product, right, the bigger the driving force. It doesn't mean it's more reactive. It just means the bigger the thermodynamic driving force. Rubidium is definitely going to be more violent, but in the end, the product isn't as stable because rubidium ions are quite big. And so they can't, the charge density is a lot lower, and interactions, electrical attractions will be a lot weaker. Did you guys have a chance to review the stuff that I've been asking? What did I ask you to review? Well, a bunch of stuff. I also asked you to look at appendix. I was wrong with appendix, right? It was appendix B. If you haven't had physics, then you need to review appendix B. Not for this. In appendix B, this is where we talk about Coulomb's law. B5, static electricity. Coulomb's law. You need to read that because that's chemistry. What is your preference, PowerPoint or board?
Either or for me.
Either or. Anybody have opinions? You can put element plus element. So for redox, we have element plus element. Single replacement. The problem with single replacement is all the exceptions. If you don't have all the exceptions memorized, then you're going to be in trouble because we're not in Chem 4 anymore. In Chem 4, they make sure the playground is small. But now, in Chem 1B, the playground has to be much larger. And so single replacement, it works if you know the exceptions. And it's fast and it's easy, but there's another way we can do it without that. Combustion, we just go to complete combustion. We have an organic carbon, hydrogen, oxygen compound that combusts CO2 and water. The alternative to single replacement would be chart. The chart method would be much easier to use. Potential diagrams are more sophisticated. Skeleton redox is chapter 5, where you balance out the redox reactions. And so let's take a look at this chart method. The chart method, this is the way the chart is in your book. And so when we look at the chart here, fluorine is up here now, F2. Fluorine is the most powerful oxidizer. You just memorize it. Most powerful oxidizer wants to take electrons. In fact, F2 wants to take 2 electrons and make two F minuses. Okay, now some people ask me, should I memorize a chart? No, don't memorize a chart, but what should you do? Whenever you're given a chart like this, you always do something. What do you do?
Read over it.
Read over it. You look for the strongest, you look for the weakest, you look for the biggest number, the smallest numbers, this type of thing, right? And then you look for kind of patterns or whatever. These numbers we're going to skip for now, but fluorine is going to have the biggest number here. The reason we're going to skip these is because of what the negative sign means. But fluorine, and then what else? What else are powerful oxidizers like fluorine? What's that?
Ozone.
Ozone. This is a very unusual species here. S2O8. S2O8 2 minus has a. It's unusual because if we use the oxidation states rules that are in chapter 3, then it comes out as a weird oxidation state. What's the oxidation state on silver?
Seven?
Plus 7?
Yeah.
Yeah. How many valence electrons does sulfur have?
6.
So it's a very unusual species, isn't it? Very unusual. Although we don't know, because the way we do oxidation states in chapter 3 is not what chapter 3 gives us. It gives us the average oxidation state. Sometimes it depends on the structure, and so we got to look at an alternate way that I'll show you of determining oxidation state. What's this one?
Peroxide.
Hydrogen peroxide. Right? Oxygen here is not -2. Oxygen here is -1. We do hydrogen first at +1, so oxygen has to be a -1. So the peroxide bond is very weak. What's this?
Is that permanganate?
That is permanganate. You should have this one drilled into your memory. MnO4- is common. This is a common oxidizer. This one's not as common. This one occurs in car batteries. What's this one called? Lead 4 oxide is the correct name for that. That's this is what we call the cathode, the car battery. We'll talk about later. This one?
Chlorine gas.
Chlorine. Chlorine gas we expect to be a powerful oxidizer, right? Chlorine, fluorine. Fluorine's more powerful. What's this called? Dichromate. Good. Manganese 4 oxide. Oxygen. Good. Iodate. Bromine. Nitrate. Nitrate's a good oxidizer. Silver ions. Silver ions are a good oxidizer as well. This is why you got to be careful handling silver salts. Silver salts stain everything black because silver ions are a good oxidizer, and that black stain is actually tiny crystals of silver metal. And so I had a student working with silver nitrate, and she came up to me after class and said, I've been washing my hands for 45 minutes, but the black stains aren't coming off. I have a job interview I'm going to right now, and she was really upset. But unfortunately, they don't wash off, those black stains. You just have to wait until the skin cells shed. So watch out for this stuff. If you get this in your eyes, that would be pretty grim, for sure. This? Iron 3. Iron 3 is a decent oxidizer.
Oxygen.
Why do we have 2 oxygens?
It's reacting with a different quantity of hydrogen and electrons
Yeah.
and forms different products.
Yeah. Which oxygen would you use? If you're going to choose one of these, which one would you use?
The one that makes water.
Yeah. The one that makes water, which is a more stable product than the one that makes hydrogen peroxide, which is a less stable product. Well, then why don't we just eliminate this? The reason we don't eliminate it is because on the other side of the table, we have the reducers. And hydrogen peroxide is a different reducer than for water. And so that's why it's there. And so if there are multiple choices, we pick the strongest. The strongest one's going to form the most stable product. Copper 2, sulfate, tin 4, sulfur, H+. So in single replacement, the oxidizer is chosen as H+ because of the pattern. But it turns out H+ isn't the strongest oxidizer, nitric acid. What is stronger? Nitrate is stronger. And so this is wrong. X is not a spectator. However, in HCl is called mineral acid. HCl, H+ would be the strongest because chloride is not an oxidizer. Chloride doesn't want any electrons. Why would nitrate want electrons? It's already got an electron. Right? Why the heck would nitrate want an electron? Why would permanganate want an electron? Why would dichromate? Dichromate's got 2 extra electrons. Why does dichromate want electrons? Do you see the pattern? The pattern here, the way to understand this is some are easy, like chlorine, fluorine. That's easy to understand why they want electrons. But something like dichromate, why would that want electrons? In fact, dichromate wants to take 6 electrons. Why the heck does it want 6 electrons? What about dichromate makes it want electrons? This is back in chapter 3. It's because this charge is the net charge. And so we have 7 oxygens. Each oxygen is 2 minus. 1, 2, 3, 4, 5, 6, 7. And so that gives us a net minus 14 charge here. And then the chromiums have to be what? Because we need this to be plus 12. Plus 12 minus 14 gives us minus 2. So chromiums must be plus 6. It's because of the chromiums. It's not because of the net charge we completely ignore. We only look at oxidation states. I could care less what the net charge is. So, for example, nitrate, just because it has a negative net charge doesn't mean it doesn't want more electrons. Nitrate wants more electrons. The same thing with this. I always ask this one. Nitrate, is electron rich or electron poor? Nitrate. It's electron poor. Why is electron poor? Because of nitrogen. Nitrogen's 5+ here. This is electron poor. Oxygen is -2. That's happy, as is. But nitrogen's +5, well, that's electron poor. But even if it has a negative charge, it's still electron poor because of the nitrogen in nitrate. Now, what about ammonium? Ammonium that's got a positive charge here. Is ammonium electron rich or electron poor? Can you burn nitrate? Will nitrate burn? Nitrate won't burn, but nitrate can cause fires. It's like asking, can I burn oxygen? Can you burn oxygen? Does oxygen burn? Is it flammable? No, but you need it because it's the oxidizer. It's 1/2 of the combustion. And so this is what happens with this. Now, is this electron rich or electron poor? Electron rich. Why? It's -3. You can burn this stuff. Ammonium burns. And so it's not the net charge, it's the oxidation states that we look at in predicting it. And so when you look at these and read through these, then you'll start to see these patterns. But the general method for the chart is easy. We inventory the species, we find the strongest oxidizer present, find the strongest reducer present. I'll do an example of this. And combine the strongest oxidizer, strongest reducer, and it yields the net ionic equation. We got to determine the driving force. The driving force for redox is different. What were the driving forces for metathesis? Gas formation is one of them. Is gas formation a driving force for redox? This is a redox reaction. So water decomposing into elements, hydrogen and oxygen. Is that a driving force, gas formation? That is, water really wants to decompose because it can form the gases, hydrogen gas and oxygen gas. Yes? So if you have a glass of water on the countertop, you better be careful because it's going to form a mixture of hydrogen and oxygen, which is very explosive. No. Gas formation, even though we form gases, does anything happen? No, gas formation is not. The reason is this. Let me just get it straight. In metathesis, the oxidation states never change. You're looking for ion combinations. Those ions retain their charge. None of the charges ever change. So we're just looking at what makes a favorable combination of charges, of ions, atoms, this kind of stuff. In redox, the oxidation states do change, and so the nature of the atom is totally different. So for example, sodium metal versus sodium ion, totally different. You know, sodium metal is very dangerous stuff. Sodium ion, is it dangerous? Have you seen the sodium? I know Kelly's seen this, but pretty soon we'll get to new stuff. But and this is a repeat of Chem 1A, except abbreviated. Just, I'm repeating this from Chem 1A because I don't know, I have it organized differently than most Chem 1A instructors. So I'm just going to repeat this. And so. See, sodium metal disposal. I don't, this video. They have the original video without all this editing on here, but I can't find it anymore. Let's show. So a lot of people say, what's the big deal? I just forgot the charge. You know, why did I lose so many points? Because I forgot the charge. Well, to chemists, it's a huge deal. You know, sodium metal and sodium ion are two totally different things. And so let's see sodium metal disposal. You know, this works. The audio works. Audio is not working.
You can sort of hear it.
Yeah, you can sort of hear it. Can you hear a little bit?
that's, there's clouds going like thousands of feet in the air on that. It's an enormous explosion. The reason why, like gas formation, precipitation, those are all minor compared to a change in the charge. A change in the charge is much more significant in terms of energetics and forming a precipitate or this. Those are much smaller. But when you have metathesis, those are the only things you can look at because the charges don't change. And so, so they didn't fix the audio yet. Okay, so what we could do is we could do something like this. Actually, there's a more involved redox chart. Let me just show you. Now, after you look at this little one that I gave you here, you should look in this appendix. This is appendix B. It has Coulomb's law, but the appendix you're going to use the most is appendix D. Appendix D is going to have some data tables here, a whole bunch of different data tables. This first data table, D2, we're going to use, actually the second data table, D2 is going to be used a lot in the next chapter. You're already familiar with appendix D2, right? You use that in Chem 1A. Oops, that's okay, this is the table D4. If you look at table D4, what do you see? You see here
Fluorine at the top.
fluorine. But you know, in the other table, what was number 2? Number 2 was ozone on our bridge table. This has, what would you call that?
Oxygen difluoride.
Oxygen difluoride. Oxygen difluoride is very unusual because what makes oxygen difluoride unusual? The oxidation states. What are the oxidation states in oxygen difluoride?
Fluoride is +1.
No. Fluorine's the most electronegative, so fluorine should go.
To the right.
No, fluorine should.
Or to the left.
No. If somebody's going to lose, would the species that loses be fluorine or be oxygen? If fluorine and oxygen got a tug of war for electrons, who would win? Fluorine, because fluorine's more electronegative. And so, what's fluorine's normal charge? -1. Fluorine's -1, making oxygen +2. Is oxygen happy at a +2? No. And so you can see this is going to be a powerful oxidizer because oxygen is going to want electrons quite a lot. And so this is the one I want to do. I want to do this. I'm going to go gold. What do you think, one of the most common charges on gold is? Gold should be
Unreactive.
well, it is unreactive. It's like fluoride. Fluoride's unreactive. Fluoride's unreactive. Fluoride's very unreactive in the redox sense, but fluoride's very reactive in the metathesis sense. The fluoridated water. I guess there was some dentist traveling in little villages in Europe somewhere, and he was looking at the villagers' teeth, and he noticed that some villagers' teeth looked good, and other villagers' teeth looked very bad, mottled, brown, decaying. The ones that were mottled, brown, and decaying, they had too much fluoride in the water. The ones that looked good had the right amount of fluoride, so he was able to determine just the right amount of fluoride to have strong, healthy teeth. It turns out that the fluoride on your teeth will, form a calcium fluoride, calcium fluoride is quite stable, and it helps prevent further decay. But anyway, getting back to this, fluoride's very unstable, gold's very unstable. What's the most reactive on this side? Do you guys remember the conjugate relationships?
Conjugate acids and bases.
Yeah, conjugate acids and bases. If the acid is strong, its conjugate base is weak. If the base is strong, its conjugate acid is weak, and vice versa. And so this is a conjugate relationship. On the left, we have oxidizers. On the right, we have reducers. If the oxidizer is very strong, its conjugate reducer is very weak. So fluoride's very weak. What's the strongest reducer? What's the strongest reducer? Lithium. So this table is big. Take a look at how big this table is. Continue on. But finally we get to lithium. Lithium is the strongest reducer. Its conjugate oxidizer is going to be weak. So this is the weakest oxidizer on the chart. This is the strongest reducer on the chart. This is how we use the chart. Well, I'm going to do a reaction, but this reaction we're going to use the this approach. I'm going to take gold. I'm going to try to dissolve gold in nitric acid. Let's see if it dissolves in nitric acid. This looks like a single replacement type reaction, but the single replacement would be wrong here because nitric acid is an oxidizing acid. Nitrate's a more powerful oxidizer. And so let's figure out how we're going to solve this. So we inventory the species in solution. Well, gold is just gold. So the inventory would look like this. One. And then we have H+, and we have nitrate, and then there's something else present in this. What else is present in this? This is HNO3 H. Water. Water is present. Sometimes water can be a reactant as well as a solvent, so we have to be careful. And we always have to include it if it's present. Okay, find the strongest oxidizer present, find the strongest reducer present. And the way we do that is we just look at the chart. We go to this chart. Actually, we have to go to the other chart as well. But gold occurs on the reducer side, so I call them RA. RA for reducing agent. Reducing agent. It's not an oxidizer. The only thing gold can do is lose electrons. H+, this is what we call an OA, oxidizing agent. Nitrate is what we call an OA as well, but nitrate has to have H+ present. And so I write this little bar here. This bar indicates that both these species are required. Because when we look at nitrate here on the chart, what else is present? Nitrate plus
Hydrogen.
Why do we need the hydrogen? Can we just forego the hydrogens? We just said, I don't want to put hydrogens there. It's like baking cookies. 1 cup of sugar, 4 cups of flour. Let's forego the 4 cups of flour. Let's go with just the 1 cup of sugar. Is it going to work? No, the same thing here. It's not going to work because we aren't going to make, if the hydrogen is not present here, we're not going to make what? Product. Water. Water is important because water is stable. And so this is why I put the bar. Do you see this bar here indicates that I need both H+ and nitrate. If the H+ is missing, am I going to make water? No. Is it going to work? No, it's not going to work. So I need that H+. And so that's why the bar here. H2O. H2O is an interesting species because H2O occurs on both sides of the chart. H2O is here. You see H2O is taking electrons, so H2O is called a oxidizer. And so H2O is an oxidizer. It's at the bottom of the chart, so does that mean it's the worst oxidizer? H2O is at the bottom Fluorine's at the top. Does that mean H2O is the worst oxidizer? No. H2O is not, because there's two charts here. H2O actually is minus 0.828, which means at minus 0.828, that puts it right here. And so that means H2O is a weaker oxidizer than Zn2+, but is a stronger oxidizer than aluminum 3+. And so H2O belongs here. Some people, on tests, they put H2O at the bottom because that's the first time they ever looked at this chart. Or they come up to me and they ask me a question, which I don't give them the answer to. Because they should know. They should have looked at the chart before and saw H2O is weird. And then here's another H2O, but hey, wait a minute. There's an H2O here. So sometimes on tests people come up, which H2O do I use? Well, you should know that already. Because you should have looked at this at least once before the test. Which H2O do you use?
Stronger one.
The stronger one. Which one is the stronger one? The bottom one or the top one?
Top.
No. That was a trick question. You would be wrong. It's not the top one. It's the bottom one. Why? Because top and bottom are irrelevant. I shouldn't have even phrased it that way, because students always come up to me and ask me that. You pick the one closest to lithium. If we're on the lithium side, you pick the one that's closest to lithium. You pick this one. Why? You pick this one because that's the stronger one. Because the strongest is here. On the right side are the reducers, right? And that would be it. And so this is the water here. Well, water turns out to be a reducing agent as well. So it's both an oxidizing agent and a reducing agent. Now we pick the strongest. Which one's stronger? We have three oxidizers. H plus alone, nitrate in H plus, or water. And so the strongest oxidizer is fluorine. The strongest oxidizer is fluorine.
So you pick the one closest to fluorine.
You pick the one closest to fluorine. Because you know what? That chart there is flipped upside down. So if you start talking about which one's higher, which one's lower, you're going to be screwed up. This chart is flipped upside down because this chart is the activity series. Take a look at the top left. That's the activity series from Chem 4. The activity series is just how strong of a reducing agent it is. This chart is the standard chart in chemistry. It's not the upside down activity series, the right side. But we pick the one closest to fluorine. Which one's closest to fluorine? So we start, this is what we do. We just start at fluorine and work our way down. We work our way down. Which one's the first one we're going to hit? Do you see it? The first one we hit is nitrate and H plus. And so this is going to be the strongest. And so it should be the most reactive. What's the strongest reducing agent present? So I put gold in there, but that means we have to go back to the book here. So what's the strongest reducing agent on the chart? Lithium. So let's work our way up and see which one we hit first out of our list. Up there. Go to the previous page here. So I'm still working my way up. Cobalt, nickel, lead, hydrogen, H2S, tin 2, copper 2. Here's water. Can I use this? Can I use this water? Should I use this water? No, I shouldn't use this water. Why?
Just don't use that in the image.
Yeah, that's still SO2. Is there any SO2 there? You can't use this because we don't have any SO2. So we'll just keep going up. Here's another water, but do we have any sulfur? We'll keep going up. Oh, here's gold. Can we use this gold? We can't use this gold because there's no chloride. The chloride acts to stabilize the gold ion. This weird species here. This weird species here is called the tetrachloroaurate ion. And the tetrachloroaurate ion is one way we can get gold to dissolve, and this is a combined reaction here. It's a combined redox reaction with something called the Lewis acid-base reaction. And the chloride is the purpose of the chloride is just acting as a base, a Lewis base. But we don't have any chloride here, so this is not going to happen. And so let's keep moving up. You remember aqua regia? Here's water. Looks like water. Is it? If we keep going up, here's gold alone. And so what's more reactive, water or gold? Water. And so this would be our reducing agent here. Well, obviously this is not going to happen. No reaction is going to happen here because nitric acid is nitric acid in water. It's not going to react with each other, right? But we're going to go through this to show you how we would do this. And so the first thing is we pick the strongest oxidizer, and then we copy the equation off the chart here. So I'm just going to copy the equation off the chart. Should have done, which is right here. Nitrate plus 4H plus 3 electrons. So I just copy that. Nitrate plus 4H plus 3 electrons yields NO plus 2H2O liquid. That was gas. Sometimes I'll leave AQ off, just to save. And then for water, I would just copy the equation off there as well. And so I go down here and go to water. What's it? Here it is. Except, I have to reverse this reaction because they don't want to write two different tables. They don't want to write an oxidizer table and a reducer table, two separate tables, because of the conjugate relationship. And so what they do is write one table. Since they write one table, we write one reaction as written here. The other reaction we have to reverse. So this is the one we have to reverse. And so this one, we're just going to reverse it because in this case, water is going to act as a reducer, so it's going to be losing electrons. So 2 waters goes to O2 gas plus 4H plus 4 electrons. You see how I just reversed that there? And so we have one gaining electrons, one losing, but there's a mismatch. This one gains 3 electrons, this one loses 4. So what do? We multiply. And so this one we're going to multiply by 4, this one will multiply by 3, and then we're just going to add them together. And so when I do this, I got 4 nitrates. 4 times 4 is 16 H plus. 4 times 3 is 12 electrons. And then I got to add these reactants as well, 6 waters. And so that takes care of all the reactants. And then let's go to the products. The products are going to be 4NO gas plus 8H2O liquid plus 3O2 gas plus 12H plus 12 electrons. And then we simplify. The 12 electrons cancel. The electrons have to cancel in a redox reaction. Electrons gained must equal electrons lost. The waters, we can also cancel those out. 6 here, that leaves us with 2 there. The H pluses, we can cancel those out. 12 H pluses, this leaves us with 4 H pluses. And so after simplifying this, this is what we end up with. We end up with 4 nitrates plus 4 H plus, actually that's it. 4 nitrates plus 4 H plus yields 4 NO plus 2 H2O plus 3 O2 gas. Okay, then what we have to do is we have to look for the oxidizer and the reducers. We have to look for driving force. So the driving force is going to be like this. When we look for the driving force, we have a competition between the product side and the reactant side. And so here, looking at this, this is what we call the oxidizer on the product side. This is what we call the reducer on the product side. I mean, on the reactant side. If this is the oxidizer, this must be the conjugate reducer. So this is a reducing agent, and this must be the conjugate oxidizer. So this would be the oxidizing agent here. And so then we can compare these here. And so looking at this, this is the oxidizer here. Okay, NO and H2O, this must be the reducer, and this must be the oxidizer here. Now, what happened to our reducer here? Because there should be water here, but it seemed to have disappeared. And so if we have an oxidizer, we also need a reducer. And what happened in this particular case is that it turns out that this is going to be both the oxidizer and the reducer. But maybe I shouldn't have done something as complicated as this. Reducer. Or we can compare it here. When we compare it here, we're comparing the 2 oxidizers. Which one's stronger, nitrate and H plus or O2 and H plus? And so let's take a look. Which one's stronger, O2 or nitrate? O2 or nitrate, which one's stronger?
In terms of oxidizer?
In terms of oxidizer.
O2.
O2. And so if we're going from a weaker oxidizer here to a stronger oxidizer here, that's unfavorable because we're going from something that's weaker means more stable to something that's stronger, which means less stable. And so we're going from more stable to less stable. Is that favorable? And the same thing with the reducer. If we look at the reducer here, now this one is a little bit more advanced because the reducer dropped out here. And it turns out that the reducer is going to be in here because the reducer is actually going to be an oxygen in nitrate. The oxygen in nitrate, it's going to go from -2. The oxidation state of this, when we look at this, is nitrogen's +5, oxygen's -2. Okay, over here, this oxygen's -2, this oxygen's -2, this one's 0. And so actually we have 12 of these oxygens. And 4 of these don't change out of the 12. I'm not going to write all 12 out. 2 of these don't change, but 6 of these do change. And so half of these oxygens in nitrate are going to lose electrons to go to oxygen. And so this is a bit more complicated, but we could do it off this. If we do it off this, which would tell us the same thing, which one's a stronger reducer? Well, because of the conjugate relationship, it's got to work like this. Water's going to be weaker, this is going to be stronger. The same thing with this. Nitrate we don't think of as a reducer agent. It's not even on the chart as a reducer. And so this is going to be stronger, this is going to be weaker. And so actually we end up with no reaction. No reaction because the reaction has to go from stronger to weaker, not weaker to stronger. So there's no driving force for this. And so this is the chart method of redox, where we just use the chart. Okay. All right. Tomorrow we'll try some examples of this. And then continue. Which book?
It's the blue one.
The
It's
blue
kind
one?
of the same. It's like aligned with that. I think it's the 10th edition.
Oh, 10th edition blue one for Chem 1B?
Yeah. Okay, thank you.
So I actually asked yesterday, I think they did this small. If they're separate output correctly, you made a note.
Yeah, okay, I'll talk about it tomorrow. Yeah. It has to do with strong electrolyte versus weak electrolyte. That's what. Strong acids versus weak acids. But at the beginning.
Sir, I was looking over the homework that you posted for the reactions. Are we sure? I have a couple questions. So, are we supposed to know all these that were posted?
What do you mean no on?
Because you posted.
Yeah.
Couple there. And like
No, you're supposed to work on all those.
Right.
Right.
Okay, so for example, for this one, how would you decide on that?
How would you do that?
Yeah.
Well, you have to figure it out. But the way you figure it out is by using one of these techniques. And so this one is what we call redox reaction.
Okay.
So you try what we just did in math. That's the way you approach it.
Okay.
Sure. Uh-huh.
We had a question.
Okay. All right, that would be the. Okay, what you'd have to show is this would be the ionic equation, and that ionic equation, you have to show the other equations as well.
Okay.
The complete equation.
Okay.
And if I look at it, yeah, right, that kind of thing. So when I look at this is not right. So you would have
Oh
fixed
yeah,
that one.
this circle is.
What do you post in your YouTube videos? How do we look those up?
Oh, okay.
Yeah.
I haven't done it yet, so
Okay.
I'll post it.
Okay. All right, thanks.
So-
How would we be able to find it?